finished up logistic population growth. We talked a little bit about metapopulations, and today I want to finish up talking about competition. So when we talk about metapopulations, remember that's typically how populations are distributed around the planet. Larger populations broken up into smaller populations, which are subsets, some big, some small. How are they connected? Migration connects them, and the rate of that migration is really important to their persistence through space and time. So is it a great idea to have your populations be rapidly connected via migration? No, because eventually what can happen if that's the case? So small populations and large populations, what happens to their rates? They will become synchronous over time. If you have rapid migration, that creates uplift and downlift at exactly the same time. So what happens if you get a disease when you're on a declining population? Every subpopulation could go extinct at the same time, leading to mass extinction event. What about the opposite of that with no migrations? Is that a good idea for species persistence? Who goes extinct there first? The small ones, because there's more opportunities, they're in more shift per unit time, or they're at the bottom of the decline, so there's more chance for them to go extinct. That isolates the larger populations who eventually will go extinct as well, because there's no recolonization from outside. So what's the best for long-term species persistence? Moderate or intermediate levels of migration, because that means small ones do go extinct. However, what can happen in the next time step?
They can recolonize.
They can become recolonized by populations that are in ascent. And so what that does, it leads to a mosaic of extinction and colonization events, but over the long haul, the overall population remains intact and the species persists in time and space. I gave you guys a model that describes those basic population dynamics, which talks about the fraction of sites occupied per unit time, whether it will increase or decrease and why. And so you should be expecting to see that on an examination and work through a simple computation to give me that information, whether it's increasing or decreasing, and what the percentile of that increase or decrease might be. Does it work, that model? What do you think? Sure it does, as long as the assumptions of the model are met. I gave you an example where they were. Do you remember what it was? The what? Prairie dogs was just an example that I gave you as a computation, but I gave you a real-world example that's been tested with the model. The bay, checker spot butterfly, and therefore the model in that particular population worked very well at predicting increases and decreases in the population size among different habitat fragmentation units. All right. That brought us to species interactions, and how they influence the abundance of organisms and increases in population and decreases in population size. So if this was a plus-plus, what would be referred to as? Mutualism. What if it was minus-minus? Competition. What if it was a plus-minus? Predation or competition. What if it was a 0+? Commensalism. What about the example of the walnut tree and the smaller trees underneath? Where the walnut tree is unaffected by the presence of the smaller trees, but the smaller trees suffer negatively. Commensalism. That would be commensalism. Very good. On examples like this, on an exam, I'll never give you the definition. Be prepared to see an example, right? Species A is doing this to species B. This would be an example of what? How's it measured in terms of the plus or the minus or the 0? Population growth rates when engaged in that interaction versus the species that would not be engaged in that interaction. So I gave you a mutualism example. What, the tick bird and the rhinos, what was that? I just gave you the answer, didn't I? It's a mutualism. All right. And we worked our way through. Commensalism one was an interesting one. Shark for more is a nice example. Cockroach and human being was another nice example of that. And I think we left off talking about disease, correct? Predation examples. So let's go back to that. And we were talking about human disease. And so human parasites are quite common. Is it more common to be a parasite or to be free-living like yourself?
Parasite.
Parasite by far. 1 to 10 is the norm. 1 to 100 or 1,000 is not abnormal. So you can have many, many different types of parasites. And human beings are no exception to that rule. Wherever you evolved that originally, well, guess what? There's parasites there to basically mirror that. So if you take a look around the globe, where do you think the most human parasites are located at? Africa, that's exactly right, because that's where we evolved. That's where our site of origin is, and so there's more parasites there that can really get into us and on us. So I started talking about some of these examples. This example on the left here is a tapeworm. Tapeworms are very common in the human population, and so there are many different types of tapeworms. You can get them from eating raw fish, you can get them from eating pork products or beef products. The most common one is the beef tapeworm, and it can get about 28 feet in length. So it can get pretty massive in fact. One of the most rapidly growing tapeworm infestations is actually the fish tapeworm. And so the way you get this thing is you get it from eating the eggs which are encysted. So in your food, the eggs are located, and then basically they're encysted, so they're protected against your stomach acids. They pass through into your intestine, where they basically hatch and then set up residence. So this thing at the top over here is a scolex. It's the head of the tapeworm. And on it there are little claws. You ever seen like the things that the climbers use to climb up the wall faces of rock, those little pecans, they hammer them in? Looks a lot like that. There's little grappling hooks and they hang into your intestinal lining like that. And then the worm dangles down and they basically eat what you do by absorbing it through their membranes externally. When you take a look, they have these segment-like structures called proglottids. You can see them up here on the left. When the worm gets large enough and they become gravid, they'll start to shed those, and they shed them in your feces. And that's how you get it, by eating the eggs that someone, unfortunately, get defecation product in your food. Most of you don't go around eating feces willingly, but unfortunately, you ever see those signs that say wash your hands? After eating or wash your hands, you're an employee in your restaurant. Well, there's a purpose for that, right? Because if you get feces on your hands, this is how you spread them to food, and then you basically spread them to other people. How do you know you have tapeworms? Well, there's a couple different ways. Probably the most common way to understand you have tapeworm is if you have onion skin-looking things in your feces that didn't eat onion. That's a surefire sign of tapeworm, so you should go to the doctor at that point. Right? How do you get rid of tapeworms? No, you can't pull them out because they'll break. Okay? You have to get wormed. Anybody wormed a dog before? Worming dogs, you give them a little pill, and they basically poop it out, right? It's not the most pleasant thing in the world, pretty disgusting. They do exactly the same thing to you. So what that pill does, is remember these things are hanging on the intestinal wall. So what this pill does is it causes you to shed the internal mucous membranes on your intestine. They're easily replaced. They're in a couple days, no big deal. What it does is it causes those little hooks to slide off, and then you'll defecate the worm out. So the way you know you have it is you see these onion skin-looking things in your poop. Unfortunately, there's a much more vicious way that many people realize they have it. And that's basically when the worm gets long enough, you're talking 28 feet, 30 feet in length. The fish tapeworm can get so long, it can get 60 feet in length. That means it can double up and twist around in your intestine and do all kinds of crazy things. And so when you defecate, you exert muscular constriction on your sphincter to push out your defecation cause. Well, if the worm is big enough, it will go and extend all the way through your digestive system. It can be extruded by that process. So then, or when you go to wipe, you feel it because it's hanging out. And then when it feels you, it doesn't like it. So what does it do? It retracts back in. Pretty nasty business, yes? So at that point, you basically fall over and you faint. And then when you wake back up, you're running to the doctor screaming that you have an alien inside you. You explain, tapeworm, here's your pills, have fun. Then the problem is you get to go home, you take the pill, and guess what? You get to defecate it out. And that means it causes stomach cramps, you sit down in the toilet, depending on the size of the worm, you got to poop it out. At that point, you look and see what came out of you, and you faint again. And then at that point, you seek psychological counseling. My brother-in-law is an avid sushi eater, and not at the best sushi places. So there's a reason why sushi chefs in Japan make a boatload of money, and that's because they're schooled for years to detect parasites in the flesh when they cut it. So if you're a ardent frequenter of Billy Bob's Sushi Shack on Hollister someplace, odds are that chef does not have the skill set necessary to tell the difference. And so you can eat this stuff and you can catch it. He's got frequent establishments like that. He got this thing. He experienced the retraction method of protection, which wasn't pleasant, and had to go through this process and ended up getting a really long worm. And so if I ever want to screw with him, if he's being a jerk about anything, we'll be at any kind of family gathering, something like that, walk up to him and I whisper in his ear, worm. That's all it takes. And he runs for cover at that point. Anything he had to say, he doesn't say it with him. So that's one thing. This thing in the middle here is a intestinal roundworm. It's another pretty nasty beast. It's very common. The tapeworm here, especially the fish one, is very common. The fish-based one is very common along the coast of the United States, obviously, because what's the number one thing we like to eat? One of the favorite foods on the coast, West Coast and East Coast? Sushi. And so, like I said, if the establishment isn't that good, you can't detect it in the flesh if you get this thing. If you cook it enough, it'll kill the eggs that are encysted. In this particular case, the middle one is intestinal roundworm, and that's another extraction. Oh, sorry, that's a tapeworm there. I want to show you another. We talked about this one, that's a tapeworm. This is the botfly, right? We talked about the botfly and its extraction, that's basically a maggot. So I want to talk about another one that's really problematic, especially along the southeast section of the United States, and that's intestinal roundworm, which is this one right here. So we have the male and the female. The female's the big one, the male's the small one. And so they're dioecious, and they live in the large intestine. Here's an example of an infestation in an intestine. These things can be really nasty depending on the severity of the infection. You get them from basically eating, again, the eggs that are found in feces, and so it has a really intricate lifestyle, which is kind of unique. So how do you get it? Well, let's say you went to eat someplace, and somebody in that particular establishment was sick and had this parasitic infection, and they had diarrhea, which is one of the symptoms, intestinal cramping, but they're at work. They go to the bathroom, they basically go to wipe themselves, and they miss or they don't wipe perfectly, and it gets on their fingers, and then you're like, that never happened to us, it does. And be realistic. And so then what happens is they don't wash their hands because they're late for their shift, or they don't wash them in hot water for long enough. And what they have is the eggs now that are in the feces underneath their fingernails typically. And so then they go and you pull up and you order your number 2's value meal or whatever it is, whatever terrible restaurant you're at that point in time. And you go home, and all of a sudden 2 weeks later you're feeling intestinal cramping and diarrhea and wondering what the hell's going on. And so this was what happened in that interim time period. So you went, you got the food, it was infected with the eggs, you eat the food, it goes through your stomach. They're again encysted, so they pass through the stomach acids, no problem. They get into your small intestine where they basically hatch. At that point, they burrow through the walls of the small intestine capillary system. They wind their way and they find their way through the circulatory system into your lungs, where they undergo a series of metamorphic development. At that point, they change their shape a little bit and they start to travel. They travel up mass through your lungs into the bronchi and into the trachea. They go up to the glottis, and at that point, the glottis is that little flap that you have. So if you ever been drinking something, someone makes you laugh and start choking or something like that. So there's a little flap there that goes back and forth between the circulatory system and the digestive system. I'm sorry, not circulatory system, respiratory system and your digestive system. So what these worms do is they poke on that little flap right there and they irritate it. And when you get an irritation in your respiratory tract right there, you guys have all been sick and you've had phlegm in your lungs from getting a cold or something, and you do this manual get rid of it, which is like that, and you bring it up, right? Well, that little thing is basically flipping the flap. It flips it open when you do that, and it allows you to get the mucus out. Well, they're triggering that response, and when you flip the flap like that, they pour out that side, the flap closes, and then they go down the digestive tract again into your esophagus, go right through the stomach acids, not a problem, through the small intestine. They set up residence in the large intestine, and then they become the adult worms, and then they undergo reproduction themselves. So depending on how many there are in your infection, it can be really bad. If they pack the intestine too much, they'll start to burrow through the intestinal walls and into your organs, often resulting in organ failure across the body. I've seen examples of this that are so bad that it results in massive organ failure. I've seen them coming out of people's noses and eyeballs and all kinds of crazy things. It's not a pleasant experience to go through. And so the infestation can be extreme. You'd be amazed at it. So just like the tapeworm, you get wormed and get rid of it. The first time that Americans actually experienced the disease in any high concentration was during the Vietnam War. And so what happened is villagers would be brought in with shrapnel wounds from all the mines that were being used. And what would happen is they'd be torn up, and when they put them on the tables, all these worms would be flooding out, right? The reason being is fertilizer is expensive. Expensive product, and our soils have been degraded all over the world because we use them too much. So we fertilize them, but since artificial fertilizer, or people don't have horses all the time and things like that, they don't have pigs, well, what's always handy is fertilizer. Human feces is, but it's never a great idea to use it because it's full of this kind of stuff. So if you use human fertilizer as a supplement in your crops, then you can pass all these diseases on quite readily, and that is what was happening. So just to show you what the infection of something like this can be, because I really want you to get the idea of how brutal it can be. It's not like a funny thing. You get wormed, and so when you're wormed, in this case, it's called a bolus. That's what comes out of you. If you got a weak stomach, you might not want to look at it, right? But this is basically the outcome of a worming, of a really heavy infestation of intestinal roundworms. Okay, so that's basically what can come. I was in that particular person. Just to put it into perspective, that's not even an adult. That's a small child, right? That's one person, and that's their infestation. That's after a worming with a particular kind of medication. So it's pretty nasty business, yeah? Not the most pleasant thing in the world. How do you avoid this kind of stuff? Should I just leave that up for the entire lecture? So, how do you avoid this kind of stuff?
Photosynthesize.
It's so easy. How can you drop your infection rate of this stuff by 90+%? Wash your hands. That's all it takes, right? If you're a decent hand washer, you will remove almost all of this stuff. Interesting enough, if you're a decent hand washer, you'll cut your cold and you'll cut your flus. Flus, not so much. Flus is more of a respiratory kind of droplet thing, but cold for sure. Because you get it on your hands, you wipe your eyes, and your mucous membrane is cool. So hand washing can really do an amazing feature. Our culture does what when we greet each other?
Shake hands.
Shake hands. Is that a good idea?
No.
One of the worst things you could possibly do. This is one of the things I really appreciate about Asian cultures, is instead of the handshake, what do they have? The bow. The bow is awesome because you don't infect anybody with anything, right? It's a great sign of respect. And ours is like, here, have all my diseases. Right? It's really kind of not the best thing. So the bow, we should all take up the bow worldwide. The diseases would be cut off like that. We do lots of really stupid things that help the spread of parasites. For instance, how many of you guys out there have dogs? Raise your hand. Okay, pretty high. Now, how many of you guys are dog kissers? Raise your hand. Hi, I'm just curious. That is a very bad idea. And I'll tell you why. There's this weird myth out there, dogs' mouths are cleaner than human mouths. You ever heard that? That's a load of crap. It's just a completely different bacterial load than ours. And dogs can do something that most humans can't, which is what?
Lick their butt.
They can lick their butts. That's exactly right. Most humans I know don't lick their butts. However, dogs do and will and can. And the problem with that is where's all this stuff coming from? A lot of it.
The butt.
From the rectum, right? The anus. And so they get it on their mouth. And so if you are a dog kisser, guess what? You're now getting it in yours. So the thing about dog kissing is, number one, is it's just freaking gross. Stop it. No one wants to see it. It's really an obnoxious thing to do. And the second thing is, you're basically, giving yourself a much better chance to get a dog's parasite. The problem is, dog parasites in humans do not match up very well because you are mammal like a dog, but your anatomy is quite different, and they get lost. And what happens is they don't mature in the places they're supposed to, and that can be very detrimental to us. So for instance, dog tapeworms get lost in human beings, and they have a different life cycle. So what happens is they're supposed to mature in the gut, but they can get lost and mature in any organ in your body, including your brain. And they create this thing called a hydatid cyst, which starts out small and then builds in size. They can get to the size of a softball. So how would you like that developing in your brain? So before it kills you, it will drive you insane at the same time. And that can all come from dogs. It's not a good idea. Cease and desist. You ever seen Jack Russell Terriers?
Yes.
They're like these little dogs about this big. They're super hyper, right? My dad has those dogs. And so they can jump like 6 feet in the air. They're crazy. And they're super hyper. And I remember one day I went over to his house, and as I knocked on the door and began to open the door, I heard the pitter-pat of little feet. And out of nowhere, I saw this dog, and it was like sailing through the air, like 6 feet. This little dog. And it was like slow motion terror. It had its tongue out, and it literally just assaulted me right in flying French kiss. And I was just like, oh God, that was disgusting. And I'm like, Dad, you gotta start reading with your dog just assaulted me with his tongue or whatever, right? Well, he's just saying that he loves you, and I'm all, dog. The dog licks his ass, Dad. And you should never let him do that that to you or her either, right? This is a horrendous thing, so please cease and desist after you. So again, the take home of this message is definitely can regulate population dynamics and not a good thing to do. So what you should do is regulate yourself by washing your hands and stop kissing your animals, all right? All right, so let's move forward now. I want to start talking about the next interaction, and that's competition. So competition by definition, again, is a negative interaction, right? You're harmed, I'm harmed if we're engaged in competition. It can occur within a species or between a species, intra or interspecifically, and it always occurs over some limitation in the resources. So the question is, well, what's the possible outcome? I know it's negative, but is it more negative for 1 versus 2? Is the negative effect equal? Is 1 almost nothing, 1 almost a lot? So that's very tricky to know what's going to happen, right? Is the competition so severe that it maybe drives one to extinction? Well, if I don't have an intuitive grasp of what's likely to happen, I have a tool that will help me by giving me predictive outcomes. What's that tool? What is it? It's mathematical constructs, right? So I can use models to give me a predictive outcome of what's likely to occur when 2 species are engaged in competitive interactions. And so that's what we're going to do. So these are the Lotka-Volterra equations. They were independently derived by Lotka in 25 and Volterra in 26. And so they're based on a model you've already seen. So take a look at that model. What is it? What is that model? That is the logistic growth model, right? So in this model, remember, what is it saying? So let's do species 1 first. The change in species size over the change in time is a function of the per capita growth rate times the species size times the proportion of carrying capacity still left to be occupied, which is denoted as K minus N over K. That's it. Is competition assumed in that model? It is. What kind? Intraspecific competition. But now we're interested in what kind of competition? Interspecific competition. So does that address it?
No.
This is the model of logistic population growth for species 2. It's exactly the same model. And it's subsuming intraspecific competition within that species. But I want to know what happens when species 1 competes with species 2, and species 2 competes with species 1. So what do we have to do in order to do that? What's that? I just need another factor that will express that, right? I have to add something to this model. All right. So in this particular case, if these 2 species are interacting, I want to know how one is affecting the population growth rate of another. So I need a term to describe interspecific competition. So that term is called a competition coefficient, right? I need this conversion factor. So it would be like this. If I want to be able to talk about them together, I need to be able to express those units so that they make sense for both species. So like an example would be if you went to a party and you walk into the party and Joe eats 3 pieces of pizza. They bring the pizza. Joe eats 3 pieces of pizza and Jane eats 1 piece of pizza. What was the impact of Joe versus Jane? It was 3 times higher. What was the effect of Joe on Jane? Or tell me, what's the effect of Jane on Joe? It's 1/3 as much, right? So Joe has 3 times the impact on Jane. Jane only has 1/3 the impact on Joe. So, but now we're speaking the same currency, right? And so that's what we have to talk about, is this exchange factor. And that's the competition coefficient. We express one in terms of the other. So the competition coefficient then can be expressed as alpha or beta. So alpha then is expressing species 2 in units of species 1, and beta is expressing species 1 in units of species 2. So this would be alpha n sub 2, beta n sub 1, right? Species 2 in units of species 1, species 1 in units of species 2. So how does it work? Well, if alpha, let's start off with the alpha competition coefficient. So if alpha is less than 1, what does that mean? It means that species 2 has less competitive effect on species 1 than what species 1 has on itself. If alpha is greater than 1, species 2 has a greater competitive effect on species 1 than species 1 has on itself. So what's the logical outcomes from that? Well, if alpha is less than 1, that means that interspecific competition is not as strong as intraspecific competition. And then if alpha is greater than 2, that means that interspecific competition is going to be bigger than the effects of intraspecific competition. Those are the logical outcomes. You can flip it and do exactly the same line of reasoning for beta. So beta, basically, if beta was less than 1, what would that mean? Species 1 has less competitive effect on species 2 than species 2 has on itself. If beta was greater than 1, that would mean that species 1 has a greater competitive effect on species 2 than 2 has on itself. It's the same basic logic, all right? So now we're just be able to talk about competition because we're able to exchange it in a currency that works for both species. And that's what this value does, all right? Expressed as 1 in the units of the other. So let's put that into the model. So we have the competition model for species 1. What is this basically saying? The change in the population size over the change in time of species 1 is a function of the per capita growth rate of 1 times the population size of 1, the fraction of carrying capacity still left to be occupied, minus the competitive effect of species 2. Why is it a minus, not a plus? Because it's a negative interaction. Is it going to increase the population growth rate or decrease it? It's going to decrease it. That's why it's negative. Okay? Let's do the same thing for species 2. So the Lotka-Volterra competition model is this. The population size, change in population size of species 2 over the time is a function of the per capita growth rate of species 2 times the population size of species 2, the fraction of carrying capacity still left to be occupied by species 2, minus the competitive effect of species 1. Make sense? So now what we have is intraspecific competition and the carrying capacity, and we have the negative impact of the other species. That's a pretty good model. All right, well, if we run that model, what are its predictions? So it has 3 basic predictions.